Today I'm going to talk about TensorFlow and PyTorch and ARM servers. The primary driver has been the availability of ARM servers with ML features that are ML specific features that are available, and there's a lot of interest in the community to run standard frameworks like TensorFlow and PyTorch. I'll try and cover as much as we can in the next 25 minutes. I am Ashok Bhatt. I am Senior Product Manager at ARM. I look after many open source projects, including the ML software stack, TensorFlow, PyTorch included. So if you have any questions, we can take it at the end when I look at the slide. So what is the agenda for today? We'll look at TensorFlow and PyTorch on ARM servers. I'm specifically going to look at CPU inference. We're not going to cover the training use case today. And within that CPU inference on ARM servers, we look at what's the end goal? I mean, what do you want to achieve as a community for TensorFlow and PyTorch? What is available today? Where are we? And here I'm going to take the end user perspective in the sense that somebody who wants to run machine learning on ARM, what is available for them? And then we look at what's being done to improve two aspects. One is usability. I mean, how easy is it to just get on with what you want to do on ARM? And how do you make it go fast? So these are kind of two different vectors, and we'll try and do that. Finally, how does anybody get involved in making improvements to either usability or performance or anything else? So there are options where you can get involved. There's already a sizable community work, so it'll be useful to have more and more community participation. So what's not being covered? We're not going to look at training. We'll also not look at machine learning using ARM plus GPU. So this is being done by NVIDIA separately. So they announced recently the entire stack being available for ARM plus GPU than GPU. So we're not going to look at that. And finally, we're still working on the availability. So I'm not going to go for any specific benchmarks or performance comparisons against x86 at this point. Okay. All right. Moving further. What is the goal? This is a loaded slide. I'll take some time to explain why this is the case. The main thing is we want ML inference solution for ARM servers, and we want that to use whatever ML specific CPU features that are available. It should be easy to use, and it should be as performant as it can, depending on the hardware available. Now, within easy to use, typically easy to use would mean I can do a Docker pull, get a container image, for example, or I would do a pip install. So I have a Python package. All I do is just pip install and magically it comes. And this option is hopefully available for all the popular ML frameworks. So we're looking at TensorFlow and PyTorch, but there are other ML frameworks as well. And the key thing is for them to support ARM as a first-class citizen, in the sense on par with other architectures. That's the ease of use. So if you do pip install or Docker pull, then usually that's how the industry kind of works in this segment. Then performance and ability to use, it depends on wide variety of inference workloads. So inference itself is kind of a broad domain. So you can do image classification, object detection. I've just listed two of them, but the list kind of goes on. You can do so many different versions of them. Each of them have their own unique operators requirement and some unique characteristics. So just because it is performant for image classification doesn't automatically mean that it will be performant for object detection, for example. And then we have the ARM architecture features. And here, one of the defining features of latest ARM-based servers is we have a large number of cores. So for example, N1, Ampere, Graviton cores, there are more than 60 cores per sock. We do have some ML specific features right now. So for example, Int8 FP16 is already available in newer N1. There are more coming like bfloat 16 and matrix multiplication, SE. They're all coming in the next generation of ARM hardware. So I've listed some of the ARM hardware there. So new verse N1, V1, which was the which is the official name for what was called Zeus before, and N2, which is official name for Perseus, both of which were announced yesterday. That's the ARM course, and then you have the partner course like Fujitsu A64FX, which is an SVE 512-bit code. Right. So first, let's look at the usability angle, right? If you're an end user, how do you get a package or a Docker image today? So I'm going to split this into three areas. First one is the Python packages itself. The goal here is, how do we quickly get a Python package or a TensorFlow package from standard repo? The standard repo could be PyPy, Conda, any of those. It's a journey. I think I'm listing out what is the current status today and what the next steps are. So as of today, this is September 2020, TensorFlow 1.15 and 2.3 package snapshots. They're available in the Linaro snapshot repo. PyTorch nightly is also available in the Linaro snapshots. This is 1.7 candidate that's available. So you could use this, and as far as we know, they have been built with the best flags that are suited for ARM. So you can quickly get started there. What are the next steps? We have to get the PyTorch snapshots first to 1.6, which is the last major release of PyTorch. And thereafter get to a point where you don't have to go to the snapshot, but you have a hosted area where you can just do maybe wget and then pip install for both TensorFlow and PyTorch. Finally, the most important one, which is to work with TensorFlow and PyTorch communities to provide AR64 ready packages. Now, you can do TensorFlow and PyTorch pip install today, but the thing is, because they have C++ code underneath them, what happens is it gets compiled on your AR64 device, which is not ideal. You want them pre-compiled with all the standard flags and everything. Just want to install. So that's the kind of the next step we're working towards there. Moving further, the other option is the Docker images. Now, within Docker images, typical solution is you have a recipe that you can build your own Docker image. So we already have a repo that's hosted by ARM, which contains the recipe to build TensorFlow for various combinations, PyTorch for one of the combination right now, and we have next steps where we will expand this to include newer releases and ACL-based configuration. Yeah, so I will talk about what ACL is and what OneDNN is later. So I'll just quickly share the screen, which contains the Docker image, and I'll explain the recipe. So this is a TensorFlow Docker recipe, and you can see that it can provide all kinds of combinations. So you can build with whether you want to build version 1 or version 2. There is different levels available, then which target you want to build. So Neos N1, ThunderX, and so on, generic and stuff. So it's quite extensive and versatile. So if you have a requirement for Docker image, then I would recommend using this recipe if you want some particular combination. If you have any requests, you can raise a issue in this GitHub repo. Moving back. So next one is a Docker image. Now, ideally, for most common use cases, you just want to do Docker pull. You don't want to sit and build an image because that's not most users do. So they just want to do a Docker pull. And here, for other architectures, it's either available with the framework group itself. So for example, Google provides TensorFlow Docker images for x86 with NV3 GPU and so on. We are slowly getting there. The first stage we are in right now is you have for a couple of options. I'll explain those options later on. For TensorFlow and PyTorch, we have it in a staging area. Now, this staging area is an area which we use to host the images before they get pulled onto kind of a Linaro's Docker Hub repo. Eventually, soon we'll get into the Linaro Docker Hub repo. But if you are keen to use, then the link is there. You can go and take a look at those. So if I quickly change, and you can look at this is the staging area I was talking about. So you have different options. You can build with ArmCL, OpenBlast, Eigen, and so on. I'll explain these options later on, but it's kind of available for you to use today. All right, what do we plan to do next? Whenever a new release comes, like TensorFlow 2.4 or 1.7 for PyTorch, we'll upgrade it. We are in the process of adding the OneDNN ArmCL option. I'll explain why that option is useful later. We are also planning to add images for Fujitsu A64FX. Right now, we only have ARM Universe N1. That's in the plans, working with Linaro in this. And we'll move the images from staging area to proper Linaro Docker repo, which would then be supported by a combination of Linaro and ARM engineers. Finally, I think the end goal, like I said in the initial, is we don't want to have a separate solution. We want to be integrated into the default standard repo. So we're kind of working with Google and PyTorch community on that. All right, so this is about the ease of use. So hopefully you can see that you can quickly get started on ARM. You have the Docker images, you have the pip packages. If you're interested, you can get started with the latest version of TensorFlow and PyTorch. I'll move track a little bit, and I'll talk about, okay, what are we doing to improve the performance? We talked about the usability in the first section. Now we're going to talk about performance. And performance using the features that are in ARM, which are useful to ML. This is kind of a map of the different open source projects that help us with performance. So you have the framework projects itself, the TensorFlow and PyTorch, and you have the library projects. I've listed 4 of them. We'll talk about them a little bit as we go along. So the framework project itself is TensorFlow. It has multiple backends in x86. So you have the Eigen backend for GBP, is the default backend. This is the one which comes when Google provides its TensorFlow Docker image. And then there's this OneDNN backend provided by Intel, which has many options, like you can do a blast via Intel MKL, or you have direct kernels via cheating, which generates target-specific kernel depending on what the hardware has. On the PyTorch, again, it has multiple backends. NNPack is kind of the default backend, but you can also use OpenBlast. And for Intel, these days, OneDNN is integrated by default with, again, same features like blast and direct kernels. In terms of libraries, this is interesting. I'll spend some time here because this has quite implications for performance. Eigen is the C++ template library that is used by TensorFlow. It has vector matrices and related algorithms. Now, this is used for 2 reasons in TensorFlow. One, just to represent internal data structures and operations. So that is independent of what library you use for acceleration. But it also uses Eigen's GBP kernel as a default CPU backend for FP32 contraction. So if you were to do a gem in TensorFlow without having any specialized library or GPU, it'll end up in this Eigen GBP kernel. We talked a little bit about OneDNN. This is Intel's machine learning acceleration open source library. It's integrated with all major frameworks. We've been working with OneDNN team to add AR64 support. We have an experimental support now. I'll talk about it further in the coming slides. ARM Compute Library, there have been many presentations today on ARM Compute Library and ArmNN. So this is our, I think, ML platform hosted. ARM contributes, partners contribute. It's an acceleration library. It has high-level operators like convolution, ReLU, name it. A lot of operators which can be used in OneDNN. So this is kind of important for servers as well, because we can use this existing investment by ARM ecosystem to make sure that the even server use cases are faster. We don't have to reinvent the wheel, in other words. Lastly, the default solution before you go into specialized operator libraries like ARM Compute Library is a BLAS, and there's an open source project which has the best performance amongst open source projects for BLAS, is OpenBLAS, which is most common, and it's already integrated with PyTorch and TensorFlow. All right, quick introduction, further details on ARM Compute Library. It's typically used with ARMNN, but you can use it on top of on its own. So that's how we are using it. So, and you have the Cortex A CPU. So this is the path we are more or less using for server work. Now, how does this map to OneDNN? So OneDNN is like an ML library. It has many backend of its own. So you can do just a simple C++ reference code backend. This is for correctness. So there's no libraries on either end, but it also has a gem backend or a BLAS backend. So there in Intel land, you have MKLML. On ARM, we have the ArmCL primitives, but to get the best performance, you end up using an intrinsic or an assembly. So that's where we plan to use the ARM Compute Library in OneDNN. So to show in a diagrammatic form what this means for two different stacks, for TensorFlow, the default option of Eigen is already available today. So you can see 2.3 and 2.2 versions which were introduced in the last 6 months. They both have well-tested Eigen implementations you can just use. So the Docker images and the packages I was talking about, they come with these two options. So you can use it with safety. And these provides decent performance. It's not super slow. Eigen GBP is a good project, and it gives good performance. So it's not super slow. What we are working on is using the OneDNN backend that's available on x86. We're adding an ARM backend to it, and we have already added the ARM performance libraries to it. It'll be part of the kind of the next release we expect in Q4 of this year. It's already part of OneDNN 1.5 release, and we expect that to be part of the next 2.4 TensorFlow release. There's a bit of a lag of when we contribute to OneDNN and when that gets picked up in TensorFlow. So this path is kind of already available, and you can get the Docker images today from the staging area that I mentioned earlier. Then we have the ARM Compute Library option. We are aiming for like the first release of next year of TensorFlow. And within that, what it gives is it gives an int8 and FP32 both options. And as of this week, we have added support to OneDNN to be able to call ARM Compute Library operators for FP32. So the next release of OneDNN 1.7 will have an ability to call ArmCL or ACL operators. And we hope to improve that over next few months. And by the time we get to end of the year, we expect it to be much higher performing than where it is today. On the PyTorch, there's a default OpenBLAS which is already available in the staging area that you can use. It's known to work well. For 1.7, that's an upcoming release. It'll still continue to be OpenBLAS backend. We are working with whatever we do for OneDNN, that will end up being integrated even with PyTorch stack. So we expect that 1.8 release, which is maybe end of the year, will have an ability to just use OneDNN. And as and when both of these projects get support for OneDNN and ACL, we'll also update the Docker images for sure, recipe Docker images for sure, and hopefully the Python packages as well. Okay, quick update on the data type. Like I said, there are many data types. We are in parallel working on adding some of the data types. As you can see, the BLAS option is usually good for FP32, but when it comes to non-FP32, like FP16, int8, and pfloat16, it's not part of a standard BLAS interface. So we plan to only do it for the ACL path. So that'll be int8. The pfloat16 is already part of ACL, as you would have seen in earlier. It's just when it's integrated with TensorFlow, we need to ensure that it is able to use ACL operators end to end. And the other thing we typically do is work with the ACL team to improve the scaling, because in edge devices, you have maximum of 8 to 10 cores, whereas in server, you have a lot of cores. So we kind of work with them to ensure that happens. All right, so with that, let me go to the final slide. And this talks about how you can get involved machine learning in ARM. The easiest way is in user. Try the Docker recipe and images. Images is a better place to start with if you are just using a standard combination. But if you want to try a different combination, then please start with the Docker recipe. If you have any issues, you can raise any questions or issues, you can raise it in that GitHub repo. ARM Compute Library is our preferred acceleration library. So anything, if you want to contribute an ARM Compute library, will end up helping servers as well as edge. So it's a Linaro hosted community project. So anybody is welcome to please work on that. If you use Docker images or recipes or Python packages, depending what performance you see for your application, we are extremely keen to know how it's working for you. This helps us focus where we spend our performance optimizations work. And to get involved for all of this, there's a weekly public meeting that I host. And this happens in 2 different time zones. Every alternative weeks, it happens in either APAC, Asia Pacific time zone, or this week, for example, it'll happen in US time zone. So the details are in that link. Please look at that link, and we'll be excited to hear your views and what your concerns, and co-work with you to move the ecosystem forward.